Manchester, easy way to do it. There are a number of different ways. Like if you get on Wikipedia, I think it shows a different way to do it that's direct with the waveform. One way to look at it though is think of it as being a reference bit. So for example, if I'm going to send this 10110001, normal Manchester would be 1 0 1 1 0 0 1, right? So transitions 1 to 0 transitions, and then 0 to 1. Now what we do for differential Manchester is we start with a reference bit, and just for the sake of argument, we will send a reference bit of 1 here. And then what we do is at each level there, if the input bit is 1, the output bit's the same as the previous output bit. If the input bit is 0, flip the output bit. So what we send is we send the 1, then this is 1, so it stays 1. Then it's 0, so it flips to 0. Then it's 1, right? So it's 1, so it stays 0. It's 1, so it stays 0. 0, so it flips to 1. 0, so it flips to 0. And 1, so it stays 0. And then we just transmit this. 1, 1, 0, 0, 0, 1, 0, 0.
All right, so you start with what?
I start with a new reference bit. That's that green reference bit that I drew
so
on
I
there.
understand if it's a 1, you're telling it to stay what it already is. 0 means switch it to the opposite of whatever your last bit was.
Right.
So what I'm trying to understand is when you wrote that second one, that's just showing what the original was?
No, this second one, this is now the differential Manchester encoded version of this, which is just regular.
Okay, so you were just showing us the second one so we knew. Okay.
So this is regular Manchester. This is differential Manchester. Okay. Now, what if we started with a reference bit of 0?
1 means switch it, 0 means maintain?
No, same thing. Now we just start, rules stay the same, but you start with 0. So now we stay the same, we switch to a 1, we stay the same, we stay the same, we switch to a 0, we stay the same, we switch back to a 1, sorry, and then we stay the same. What do you notice about this one versus that one? Yeah, it's just going to be exactly the opposite, right? So it's just going to be a flipped version of the same thing. Okay, I'm glad you asked that. What's the advantage of this? Okay, so we did an output. We did the example here. There's one in your slides that you look at. What is the advantage of this? Anybody know? It's no longer vulnerable to phase slips like it was before. That's the main reason. We do have to send a reference bit, so there's one extra thing. Wait, just a second. Let me show you. Now all right, here we go. Differential Manchester, sometimes they call it BMC, which is biphase mark code. Okay, transition is guaranteed at least every 1 bit, which we already had with Manchester. Detecting transitions, less error coding. So, unlike with Manchester, only the presence of a transition is important, not the polarity. So, for example, if we swapped the wires, you notice these, it would just be an exactly inverted version of the same thing. The differential code would still work exactly the same. See why that works?
So actually here you can turn a 0 into a 1.
There it is.
Oh.
Had to do it.
Couldn't resist, man.
Oh, man.
And Dr. Jackson's like, I don't get it. Don't worry about it.
I'm guessing that's something out of math where 0 equals 1.
So,
All right. So what happens is it doesn't matter which of these gets sent, right? Because now if we decode this back to our original thing, with either of these, we're going to get here, we start with a 1, and then there's not a transition, so that's a 1. There is a transition, so that's a 0. Not a transition, not a transition, there is a transition, there is a transition, and there's not a transition. So it actually always decodes back to this original thing regardless of which of these gets sent. So if we screw up and attach our wires backwards, it just doesn't matter. It's only the presence of the transition that tells us whether it's a 1 or a 0.
okay. Well, I'm sorry, just pending a second. There was a transition. There was a transition.
I think it's hard because without actually putting the
Yeah,
time
I
blocks,
can't- I'm trying to tell,
Well,
like,
okay,
where-
here,
it makes
let
it
me-
kind of hard to follow.
All right. So this is the edge. Okay, this is the edge of the. Wait. Okay, so there. That's the center. 0. This is the edge. 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 Okay. So now on those green dotted lines, you'll notice that now, look, if there's not a transition here, that's going to be a 1. If there is a transition here along this line, 0. There's not a transition, so that's a 1. There's not a transition, so that's a 1. There's not a. Whoops, did I
Wait,
draw
no,
that wrong?
you just said 2 different things here.
Wait, why are you saying I did 2 different things?
Well, no, like on that first one you said there's not a transition because it's a line. The second one you said there is a transition, but then the next one you said there's not a transition.
Oh, no. Here there's not a transition
Right,
right
there's
here
not
because
one there.
there's no gap. So there's not a transition.
Those are
And
one.
here there is,
So
that's a 0.
the next one,
Next one.
there is.
Oh yeah, wait a minute. What am I doing wrong here?
Oh my god. Your cycle's not split.
Right now.
Oh yeah, no, never mind. I was trying to take a shortcut there and it's not working. But it's just the presence or absence of a transition. So if there's a presence of a transition, that tells me that I have 2 things in a row, right?
Right, can you just like put your finger on there and show where you're counting the transition? Because that's where I think I'm getting lost at.
Okay, now look, down the center here, everybody realizes that if we start with a 0, it's just going to be flipped, right? So I can erase this. Okay, now let's take a look at this. We've got 1, which is high to low, then this thing, lead balloon. All right, this one, now every time we have a 1, we stay the same, so it stays 1. Then when we have a 0, we flip.
Right.
We have a 1, so it stays the same. A 1, so it stays the same. We draw. So 0 here is flip. 1 stays the same. 1 stays the same. 0 flips. 0 flips. 1 stays the same. Right? And 1 stays the same. Okay, now the transitions here along the edge, So 1 is 1 to 0. 0 is, let's move this over so it's a little more in the middle. 0 goes 0 to 1. 0 goes 0 to 1. 0 goes 0 to 1. 1 goes 1 to 0. Then 0 to 1. And 0 to 1. Okay? So these right here, 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 and here, those are what are actually representing the bits. Okay?
Okay.
Now, the cool thing about this, though, since it's differential, we can actually pay attention to what's going on in between. We know when it's a 0, that means it stays the same. I mean, excuse me, when it's a 1, it stays the same. So our original 1 here, every time there's a 1, it stays the same. So that means if it stays the same, there is going to be a transition on the boundary, right? So now if we go along on the boundary here, if there is a transition there, let's write a 1. If there's not a transition on the boundary, let's write a 0. Okay? There is a transition on the boundary. There is a transition on the boundary. There's not, and there is. And look at that.
Okay.
That's our original thing back just by reading the boundaries. So now it doesn't even matter which direction it goes. It's just whether there's a transition there or not. And so now all we need to do is detect those boundaries. If it's differentially encoded, we just detect the boundaries, and if there is a transition, it's a 1. If there's not a transition, it's a 0. Does that make sense now? A little more? Kind of.
If the edge is going down, then it's going to be a 1. If the edge is going up.
No, for differential, it matters not at all. If there is an edge at all, it's a 1. And if there's not an edge, it's a 0. On the transition, right? But you're right, we encode it still as a 0 is a transition going up and a 1 is a transition going down. But even that doesn't matter. If we're doing differential, we could have done it either way, and now it doesn't matter.
The knowing when, I mean, we just had all this problem of knowing where the break is. That's all
Right.
timed.
That's all timed, and that's the phase-locked loop keeps that in. And we'll come back and talk a little bit more about phase-locked loops. So, okay, so that's differential Manchester.
Can you just go over the change one more time?
The change from what?
From the original.
From the original to differential.
Yeah, from
Okay.
regular to differential.
All right, so regular Manchester, every time we have a 1, it's a transition from 1 to 0, right? Then at the bit boundary, we get in place to do the next transition.
Hold on, what you just said from 1 to 0, but we got 1 here, right?
I'm sorry, let me rephrase that. We've got 2 voltages, a high voltage and a low voltage, right?
Alright.
So a 1 is a transition from high to low voltage.
Okay.
A 0 is a transition from low to high voltage.
Alright.
And then whether or not there's a transition on the bit boundary in between the bits depends on whether we needed to get in place to go down to up again, right? Okay, so now to do differential, what we do is we put 1 extra bit on the front of it. Okay, it can be a 1 or 0, it doesn't matter. We'll say it's a 1. And then every time we take our initial value, and if that's a 1, we don't flip this, we just leave it a 1. Every time this is a 0, we flip from the previous bit to the current bit. So since this is a 0, we flip from 1 to 0. Since this is a 1, we don't flip, so we stay a 0. Since this is a 1, we don't flip this bit, and we stay a 0. Since this is a 0, we do flip it to a 1. This is a 0, so we do flip it back to a 0. And then this is a 1, so we stay a 0. So this, the original code tells you flip or not, and the previous bit tells you what to flip to, right? And then the nice thing about this is once you've done this, we, instead of reading on what was the center of the bit and having to determine the direction, we just read on what was the bit boundaries, and it's just presence or absence of a transition tells us whether it's 1 or 0. Okay, so that's differential Manchester. Then very briefly, let's do BAMI. Mark and space. A 0 is a space, a 1 is a mark. There's no unipolar form because you can't do alternate marks, right? So it doesn't work in optical. Since it's an alternating mark, the average DC value is 0, right? Why is that important? Why do we want our average DC value to be 0?
Is that like what we were talking about before? It's easier to go positive or negative?
Right, okay, it's easier to go
Same
positive
thing.
or negative. Other thing is, we don't want to be shoveling a lot of current down the wire. We want it to be essentially stopped on average, right? Well, and think about wireless. How do you send DC over wireless? You can't, right? So if there is an average DC value, then we can't even send it over wireless. Okay, so discrimination threshold. Problem with this is we need 2 thresholds. One to discriminate the positive marks, one to discriminate the negative marks. It's totally independent of content, and it's easy to adapt to a changing attenuation. If we get string of zeros, we still don't have transitions. Couple things. The problem with it, though, is if we have a string of zeros, we don't have transitions. So the way to solve that is replace long strings of zeros with something that does have transitions. Seems like it would just be easier to use Manchester, but whatever. Here, if we have k consecutive zeros, we replace it with an illegal BAMI sequence. So, for example, we have some possibilities. B6ZS, we replace 1 followed by a string of 6 zeros with 1, 0, violation, B, 0, violation, B, where B is just regular marks. I'll show you an example here in just a second. Okay, B8ZS, we replace 1 followed by 8 Z's by 1, 0, 0, 0 VB, 0 VB. So it's the same as B6ZS, but we just leave the 2 extra zeros in there. And then B3ZS, which is what a T3 line uses, V's have alternating polarity. So a 0, 0, 0 becomes 0, 0 V if there's an odd number of 1s since the last V, and 0, 0, 0 becomes B0 V if there's an even number of 1s. So let's look at an example. I realize that's, you're like, what the crap is this going on here? Let's look at an example. Okay.
Hey, hold on. Can you tell us what B and B stands for?
Yes, B and V is a violation. So, for example, here, let me just let's draw this on the board. If I had 1, 0, 0, 0. Well, first off, let's do 1, 0, 1, 1, 2, 3, 4, 5, 6, 1, 0. Okay. And I wanted to encode that in normal BAMI. I would have 1 is a high voltage, then 0, then the next one is a low voltage, then zeros are all just 0, then the next one goes to high, and 0 is in the middle, right? Because it's alternate mark. We have a positive mark, then a negative mark, then a positive mark, right? Now, for B6ZS, we want to replace this with 1, 0, V, 0, B, 0, Whoops. 1, 2, 3, 4, 5, 6. What did I just do wrong there?
They don't have a B between, or 0 between the V and the B.
Oh,
It's not Bob.
it's not Bob, it's just VB. Thank you.
Bobo.
0 VB, 0 VB. Okay? So let's graph that out. We've got 1, 0. So this is 1, goes down, right? So now we have 0. Now we need to do a V. What would I do for V? Craziness. No. V, a violation is it goes down again. And then B means it goes up. Now, violation means it's going to go up and then down, back to 0. And then now, my next one is going to go up again.
Oh, okay. Violation, because that's against the. what
It's
the
against,
code is.
it should go up
Up,
if it
yeah.
were a 1, but now it's a 0. So every time the receiver sees a violation, it knows, okay, that's something screwy. That was probably, it's supposed to be a 0. And you'll notice it ends up being this nice little, we've got 1, 0, and then it's got this pattern that's symmetrical.
Will it always end up that way?
It'll always end up that way. I mean, it might be upside down. If this one had been
Oh,
up,
yeah, I just meant,
but
because I
yeah,
was about to ask, that next one, does it go off of your last B, or does it go off that original one?
it goes up. It goes
but
off
if it's
of.
symmetrical, it doesn't matter.
Yeah, it doesn't matter, but it's going to go off the last B.
So, the violation is whenever it just skips from minimum voltage to maximum voltage, and it goes to 0.
No. Other way around. It should. Okay, so marks. Let's say this is 0. This is plus V and minus V. It should go plus V, 0, minus V, plus V, minus V. It should always alternate, right? Like if this was 0, 1, 0, 1, 1, 1, it should look like that. So a violation is if it goes from 0 to 1 and then went up again. This one's a violation. It's got to go down the next time after it went up. Okay.
I see what it's positive, negative, negative, but is it dependent on what it was in front of it? So like right here, when you got violation,
Right.
Is it going? It's because there's 0 in front, right? That's why it should be going
Right.
up.
So for example, let's say that originally that this 0, that this one had been going down. Okay. So what if we had this green one? It goes down, 0, up, 0, down 0. Okay. So that green one would be the other case, right? If we happen to be on a down like that, then our BAMI, the B6ZS would go down here, then this one would go up, then it would go to 0, and now it's going to go up again because this is our first violation. Up, down, back to 0, and now instead of up, down, it's going to go down, up, back to 0, and then this one is going to go down. So you'll notice that this ends up the same. The actual ones end up the same. Whoops, I should have drawn the around green one. The actual ones end up the same as they were. The only difference is in this section of zeros, we get a big. All right, so. Let's, and the way that it works out,
Give me a Smith chart.
yeah, Smith,
I want the Smith chart.
exactly. Yeah, the PLL needs some transitions, so if we have a long string of zeros, we need to put some transitions in there, and that's all this is for.
Yeah, the B3ZS, that one.
B3ZS is a little more complicated. So,
How long did it take us to get that one?
all right, let's say that we have age XXX, okay? There's 27 possible XXX sequences from 001 to 111. There's 00L, 0L0, 0LH, L00, L0H, LH0, and LHL. Those are all the valid codes. We've got 3 bits, or 3 values, so there could be 27 possible things, but only 7 of them are valid. And you can tell they're valid because they all have an alternation. Anytime there's a low or a high, they alternate, right? So these don't matter. They 00L, 0L0, and L00. Those could be anything, but those are valid. But anytime there's 2 marks, they alternate. LH, 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 LHL. Well, oh yeah, no. All we're saying is, if I have 3 values, I can go high, low, 0. So here's my 3 X's, right? But I can't go high, high, 0. That's not a valid BAMI code. This is still all BAMI. This is BAMI for B3ZS. Alright, so 000 must be replaced by 00H if there was an odd number of ones since the last violation. L0L if there was an even number of ones. The other 18 sequences are invalid, so it only uses 33% of the possible code words. So 53% is unused, so then we can do some other stuff with it. You know what? I am gonna just let's make an executive decision to ignore B3ZS. We have talked about it, but from now on, let's ignore it. All right. Other possibility. What's that?
Is it even really used? Or I mean,
Yeah. Yeah, that's actually the one that's most used. That's used in T3 lines. B6ZS was used in T2, which is not even a thing anymore.
Great, so the one we get is the one we use.
Well, no, but B8ZS is used in ISDN. I mean, this isn't that complicated. Let's take a look really quick. It is in the book. Yeah, it's easy enough to look. The general idea is if we get 3 zeros in a row, let's use this same thing but with a B3ZS, okay?
Okay.
Let's assume
We have to know that BP.
This is chapter 3, right?
You gotta know all of this.
this is, well, it's in this,
Oh, the reading you have?
yeah, the reading is written on the board, but it's underneath there. This stuff is in, just a second, Beasley 2.1 to 2.4, 3.1 to 3.2, 4.1, 5.1 to 5.4, 5.8, 5.9, 6.1, 6.4, and 6.6. It's in, yeah, well, that's what we're trying to get to here. Yeah. Okay, let's just do this really quickly. This can't be 0, 0, 0. Let's say that there's, let's say there was a violation out here beforehand, okay? So now we have an even number of ones since the last violation. So we've got, there was a violation, now there's 1, 0, 1. Now we replace this, since there was an even number of ones, we replace this with L, 0, L. So we go L, 0, L. Now there's been an even number of ones since the last violation, right? So we go L, 0, L again. And now we go, well, that was supposed to be, and then we go high for that 1 and back to 0. LOL indeed.
So you look at every set of 3 zeros, and you just look at how many ones there have been since the
How many
last
ones
V.
since the last V? Or since
So,
the...
and V would be used if we, well, how are you going to have V's? Like those, are those L's? Because you have a low, low, zero, low, those are violations, aren't they?
Yeah, this is actually V0V, and then this is V0B, and that's B, right?
Would it really be V? I mean, to me, really, because it looks like V0V.
It is V0B.
V. It looks
V0V.
Because
Oh,
remember
no.
before when we had a violation, the B fixed itself. And
Oh.
here you had a violation, and it looks like you just did another violation because you did low, zero, low. So it's
Right.
two violations in a row.
Actually, yeah, in this case, yeah, I guess you're right in that case.
And
Would be
then, so
V0V.
if you had 0, 1 since the last violation, that's considered even?
Yeah.
Okay.
Okay, one other thing. Next way that we can do line coding is do multiple levels. Instead of having -1 and 1 here, binary, we can have 4 array. So we have -3, +3, +1, -1, and 0, right?
Okay.
So what does that allow us to do?
You can do 0, 0, 0, 1, 1, 0, and 1, 1.
Right.
Hey!
Pair them up. 0, 0, 1, 1, 1, 0, 0, 1. So now, in the same amount of time and same amount of bandwidth, we can have double the bandwidth in the same number of pulses. So it's lower signal power, so it means it takes lower bandwidth. One example, if we're doing 10 keystrokes per second via a UART, does anybody know what a UART is? Yeah, it's been a while. Universal Asynchronous Receiver Transmitter. That's one of the things that like your keyboard is attached to your computer via that. So if we're using 7-bit ASCII, that's 70 bits per second that needs to be sent through. But our line rate, because we have a 12-bit UART, is 120 bits per second. Then if we do a 4-level code, then we've got 2 data bits per symbol, so we can do that in 60 bits per second. So 60 baud, how many of you have heard like of a 14.4 baud modem, or a 300 baud modem? 300 baud modem doesn't mean 300 bits per second modem. It means 300 symbols per second. And that would be, if we do 2 data bits per symbol, if we have a 4-level code, 60 baud would be 120 bits per second. So in this example, we've got 120 bits per second is required, but if we send 2 data bits per symbol, we only need to send 60 symbols every second. So that means we only use half the bandwidth. So looking at this, it ends up with our delta signal power versus unipolar is negative 9.5 dB, so it's much better signal power, 6.5 less than the noise power. So our signal to noise ratio goes down by 6.5 dB. 16-level codes would be 4 data bits per line symbol. If we wanted to have 8 data bits per line symbol, how many codes would we have? 32, right? So similarly, that 16-level code drops us to 30 baud, gets us to minus 23 dB or minus 17 dB for the signal-to-noise ratio. So the difficulty with that is our signal-to-noise ratio goes down when we do this, right? Goes down by 6.5 dB for a 4-level code, 17.5 dB for a 16-level code. We're going to see this. How many of you know what QAM is? QAM? Quadrature amplitude modulation, which is going to be the way that all the wireless stuff that we talk about mostly does its multiple bits per symbol. The problem with that, when you add bits per symbol, just like this, our signal to noise ratio goes down. So what does that tell us? If we've got a required signal to noise ratio at the end, then we better have it better to start with, right?
Can we do another example of that again?
Okay, well let's do this. Well, let's take a look at this. This is ISDN over analog twisted pairs. This is the same basic thing, right? This is an example of what we're talking about there.
2B plus D.
So 2 ISDN B channels plus a D channel.
When are we going to cover channel? Future?
Like Monday.
I just want
Yeah.
to know, do I ask now or you're like...
I'll tell you now, but we will cover this. A
Okay.
B channel is 64K bits per second. So we have 2 B channels, which are 64K bits per second, and a D channel is 16K bits per second. It's just a control channel usually, and that's what ISDN calls them now. What's that?
As the letters go up,
They
rate
they
is
get
going.
yeah.
So theoretically, like a C would be, what, 36?
If there was one, it would probably be 32.
Oh, there
Yeah,
isn't one.
there isn't one. There's just B and D.
Okay.
Okay, so B channel is 8K, 8 bits. You send 8K samples per second, so we're sending 8 bits plus 8 bits plus 2 bits gives us 144K bits per second. Does this number sound slightly familiar to people?
No.
144K bits per second.
14.4.
Ah, 14.4 modems sound familiar to anybody? Yeah, that's and then 28.8, and then 56, right? Remember those, all those numbers? That you'll see where a lot of those came from. So we've got 2 guard band bits, which means we end up at 160K. Now, what we can do is use what's called the 2B1Q 4-level line code. So here's where, think of this, we won't define 4-level line code, but we've got, it's just like this one. Here's a 4-level line code, right? 4-level code has 2 data bits per line symbol. So if we use a 4-level line code, that means we can send 80K symbols per second to get our 160K bits per second, right? So our 16K bits per second to spare is those 2 guard band bits, and that gives us a 10% guard band. And then modems work pretty much the same way. All right. I know I'm going to regret saying this, but does everybody kind of see what we were getting at there? I realize we just kind of burned through quite a bit of stuff, but the basic, let's go over the basic points. Basic points are there's a number of different ways to line code. There's return to 0, non-return to 0, Manchester, differential Manchester, and BAMI are the ones that we talked about. Manchester, big advantage of it is what?
It has a change for everyone.
There's always transitions, so our PLL stays the
You
same.
have to worry about a phase shift.
Right. But you have to worry about phase shift. So differential Manchester does what for us?
See, I know you said you don't have to worry about that, but I just don't see why. I still can see where you could have a shift and it eventually could go out of line.
That's
It's
true.
messed
You
up,
could have a
so-
shift and get out of line, but see the problem, what happens is with differential Manchester, there's always a transition at every edge. On every bit center. There's not always a transition on the edge. So if we're just getting transition, at least you eventually notice, it's detectable that we're off phase. Regular Manchester, there's no way to detect that you're off phase. You're just going to flip every bit. Differential Manchester, the way to detect it is if you keep getting strings of transitions every time, you're off phase. You shouldn't have a transition all the time. You should have gaps.
Will we ever have to make a decision on what type triggers? Or is that
Probably
designed by
not. That's
manufacturer?
built in. That's set at the manufacturer and built into it. Now you may have to decide what things would be best. What box you want to buy for a particular situation. But in practice, you're going to be dealing more with different modulation methods like PSK, FSK, QAM, all of that kind of stuff. This is kind of the base level of that. What we're trying to get at is that we can code things in ways that make sense for the channel that we're sending them through, right? Instead of just having square pulses, we want to change the characteristics of what we're sending so that they have better signal and better power characteristics that match the channel better. That's what all of this boils down to. Then we talked about BAMI. Main thing about BAMI is it doesn't have transitions if there's strings of zeros. So we talked about adding in violations so that there would be transitions. Then we talked about multi-level line codes, which improve your bandwidth. I mean, that doubles the bandwidth every time you put more levels on there. But the negative side is it reduces your signal to noise ratio. So if you're going to have more bits per symbol, you need to have better SNR to start with.
How do you convert back from like a symbol rate to you get your symbol rate and you want to calculate your data rate? I know we've heard over that. I'm only asking because
No, that's fair.
So we gotta figure out what is the bits per symbol?
If we've got,
yeah, because we get our data transmission.
you've
rate.
got to know how many bits per symbol times number of symbols
Yeah, number of
per
symbols.
second is going to give you BPS, bits per second, right?
Yeah.
So
I'm only asking because when we get like data rates for like a TDM mesh from Battle Lab, they give them 2 mega symbols per second.
right.
Everybody asks, what the heck is that? What
And
the heck
bits
is
per symbol is just going to be log 2 of the number of levels, right?
Okay.
So if you have 2 levels, there's 1 bit per symbol.
So it depends on how many levels whoever we're getting our
Right.
pipes from is using.
Right. And then this symbols per second is baud. So what we can do is BPS is just going to be log 2 of levels times baud will give you the number of bits per second. Does that make sense?
Yeah, it's a question that a colonel was asking.
Oh, okay. Good. Fair enough. All right, let's take a short break because we haven't had one